today with one of the first talks. I want to thank you all for coming to my talk, and I want to thank everyone that is calling in remotely and everyone that's helped organize Kotlin Conf today. I hope today to help you unlock more power of Arrow 2.0. I'm Simon, I am from Belgium, and I've been working with Kotlin since 2015. I've worked on the back end, on the front end, with functional programming, object-oriented programming, and a mixture of both. I've involved in a lot of open source projects, but the best known is probably Arrow. You can find me on Twitter and LinkedIn, and I also want to refer you to the really nice documentation that we heavily worked on in the last year. So, why Arrow in Kotlin? Kotlin already offers us a lot of amazing features to write elegant and type-safe code. But sometimes we want to take that further, and that's where Arrow comes in. So, today I'm going to be talking exclusively about DSLs in Arrow, and I want to recap and review what DSLs can do. And I want to start with the smallest module in Arrow, which is the AutoClose DSL. And the AutoClose DSL is built on the new multi-platform autoclosable type from Kotlin 1.8. And if you read the autoclosable documentation, it states that a single abstract method close is not recommended to be used directly. And instead, Kotlin recommends the use method. And then we have two independent resources, like our data source and a tracing type. We need to nest these blocks. And this introduces callback hell the more we need independent resources. But we can fix this callback hell with a DSL. So the AutoClose scope DSL looks like this. It gives us an install function that we can use to install autoclosables in an imperative way in a DSL. So how does that work? DSL works using DSL builders. And this is probably the best known DSL builder in the Kotlin ecosystem, the Kotlin Coroutines run blocking function. And if you're familiar with structured concurrency, you might know that the coroutine scope type is what allows us to call launch and async. And the autoclose scope function looks like this. So it replaces coroutine scope for an autoclose scope type. So what does the autoclose scope type allow us to do? We can, of course, see the install method, which we just saw in our DSL, that allows installing autoclosable types, and that will make sure that their close method is called when DSL finishes or an exception occurs. But all DSLs, in my opinion, should be optimized for third-party types. So there's also a single abstract method that allows you to integrate types that do not implement autoclosable. And that is really useful for targets that are not JVM, that typically do not implement autoclosable types. So there's no need to wrap your types to implement autoclosable. So now if you look back at the DSL, we can see that our install function comes from the interface. So we've replaced callback hell with a simple function and a simple interface. So to conclude, the autoclose scope DSL gives us the same guarantees as autoclosable.use, but it allows us to write imperative code without nesting. It allows you to integrate your own third-party types without wrapping or implementing the autoclosable type. It's a very small and concise module with no dependencies, and it is really feature-focused. So that brings us back to our overview and probably to the best-known library in the Arrow ecosystem, Arrow Core. And Arrow Core has some fundamental types like either, non-empty collections, option, tuples, etc. But I do not want to talk about those today. I want to talk about the DSL. But if you're familiar with Arrow and its long history, you might know that a lot of types and APIs have been removed in Arrow 2.0. It's left some people in the dark, and we really didn't want to do that. So when we were announcing these features in Arrow, the Quiver library was released by Cash App. And the Quiver library adds more functional operations on top of Arrow. So this was the perfect opportunity for everyone to move these deprecated APIs to the Quiver library such that everyone can continue working in their preferred style. So I want to start by talking about typed error handling by using exceptions, right? So type error handling is maybe Arrow's most loved, but also its most controversial feature. So today we're going to be building a premium user registration flow. And when we have to insert our user, this can result in a unique violation with exceptions that might look something like this, right? So we have a user exists runtime exception, and we stop our method to immediately throw the unique violation. So I think this is the most used style in both Kotlin and Java, but there are some caveats. So we can simply try catch our code, catch the user exists exception, and recover from it. This is pretty fundamental behavior that I think everyone is familiar with. But Kotlin doesn't have checked exceptions, so there's really no way to make sure that this is actually ever handled. And hopefully you've written tests and this will still be caught before production, but maybe you want to shorten the feedback cycle from testing to compile time, or maybe you just want to protect crucial features or explicitly type your errors. There are many reasons why you might want to use them. So how does this work? Again, a single abstract method interface, the raise interface, which allows you to raise an error into the DSL. And since you raise an error, it never returns a value, so it returns nothing. So how can we use this type? Here we have our user exists error, and it no longer is a runtime exception. So we are free to model our errors however we want without having to participate in a throwable hierarchy. We can also see that we've introduced an extension receiver for the raise type, which I'm not super happy about, but we'll see what we can do about that later. And we see that we replaced our throws function with the raise function. So if you ignore the raise in the extension receiver, this almost looks like the exception-based code. So one of the solutions that we can use to remove it from the extension receiver is to move it to the context parameter. And initially, this might not seem like a significant improvement, but we'll see down the line how more important and powerful this becomes. And while I am super excited about context parameters, I also want to emphasize they will not allow us to take shortcuts. So we still have to think about all the principles that we find important to write maintainable and clean code. So now that we've defined these functions, how do we call them? Of course, again, a DSL builder. But this time, the DSL builder requires two lambdas. One, to run the actual program, which might raise an error, and a second lambda to recover from that error. So you can never run a raise program without handling the error, right? So this is almost like checked exceptions, but without the throwable hierarchy. So this is an example of how we can insert our user and recover from our user exists error, right? So our recover DSL builder brings into scope the raise as long as we handle the potential error. And here we return a default value of null, so we've effectively implemented insert user or null. So when should you use exceptions and when typed error handling? First of all, I want to say there's no wrong answer. Right? You should do what you find best for your applications. But if you do want to use typed error handling, there's a general rule of thumb that works very well. When things are truly exceptional, like thread death or virtual machine error, we typically do want them as part of our domain. Similarly, for unexpected exceptions, like the network being down, we also do not care for those in our domain. So we only want to protect things that are part of our user flow or part of our business domain. Things like a unique violation. So how can we implement this? Right, so here we wrap our database code in try catch, and we attempt to catch all SQL exceptions. And if an SQL exception occurs, we're going to check if it's a unique violation, and in that case, we are going to reify it into the race context. And all the other exceptions will be rethrown, so they can be propagated for example, resilience, which we will see later. So how can we model our errors? When we no longer have to extend from a throwable hierarchy, it seems that we almost immediately reach out to sealed hierarchies. You could define a single sealed hierarchy for your entire application, but that typically doesn't scale very well. So we typically split our code based on use cases or domains or whatever architecture you might be using. And then we still need to bring those types together, and we use a technique that I call layering. And we will also see how context parameters will allow us to completely get rid of the need for layering. So this is our user error domain. It's a simple sealed hierarchy that contains our user exists unique violation and a new error or username missing. And the username missing error occurs when we try to retrieve the username from the HTTP request. In the case that it's not present, we raise a username missing error. And in the case that it's present, we return a valid username as a string. We create a new separate domain for our payments. So we create a payment error, and we here, as an example, take into account two critical errors: a credit card expired or insufficient funds on a credit card. And a function for receiving our payment might look like this. Here we have, again, an extension function on user. And here I also want to note the context receiver is allowing us to define elegant syntax on the user while still taking into account a potential error. And in this case, in case the payment is successful, we don't return anything, and in case it goes wrong, we will see a payment error in the context. And imagine this is using any third-party payment service that you are currently using. So how do we bring these different types together? Right? We somehow need to bring these different error domains together. And it's a technique that I've called layering. There might be different terms out there, but we have defined different domains, and we now need to define a kind of service layer that brings these different domains together. So I define a service layer error for our user registration flow, and our user registration flow can result in a user error or a payment error. So this is really neat because we are using inheritance and subtyping to bring these different worlds together. We can then define a function. I'm again using extension receiver because we are working here without context parameters. Right? And we define a route handler, so it takes a request, it runs a response, and it can potentially result in a user registration error. So all of our user errors and all of our payment errors. Which means that inside of the function body, we can call all the functions we've defined in an imperative normal way. So if you look simply at this function body, you might never know that this is actually using race behind the scenes. We are writing simple vanilla Kotlin code. But in reality, a lot is going on here. Because our username potentially raises a username missing, our insert user potentially results in the unique violation, and receiving the payment can result in the expired card or the insufficient funds error. And when everything goes wrong, we simply return a created response. And I want to emphasize here that this is very interesting because race respects the subtyping defined in our layered sealed interface. Context parameters will completely free us for the need of layering. This is extremely powerful. Within the context parameters, we can define independent errors of each other. And that means that we no longer have to create a common parent, but that also means that we can handle individual errors wherever in our entire program. And this is typically very hard to do with more traditional approaches. And we can also see that our function body stayed exactly the same as before. this is my personal opinion, but I feel that the raised DSL truly elegantly fits into the language. Because if we squint our eyes, you might see that nullable types relate to option, but in kind of a flattened way. We can also see how structured concurrency and suspend allows us to flatten types like mono from Reactor, single from Eric's Java, completable future, and any third-party type that you might find out there. For those that have never seen this, the Kotlin Flow Builder is actually also a DSL like we've been defining throughout this entire talk. Right? So it has a single abstract method interface, flow collector, and it allows us to emit values into a stream in an imperative way. And finally, context parameters seem to really double down on these patterns and give us so much more powers to define these kinds of DSLs, not only for library authors, but also for end users. So here's an example of the structured concurrency DSL, where we can flatten the reactor type with await single, of completable future from Redis, the Kotlin Coroutines delay function, and a third-party async type. And we see none of the complexity that is happening behind the scenes. And actually, combining 4 different concurrency frameworks is extremely hard and error-prone to do. So this is like a superpower that we can imperatively combine all these different frameworks. So I feel that the raised DSL does a very similar thing. So we define our race in the context, and inside of the function body, we can integrate with either or with the third-party type coming from Quiver or any third-party type you might have defined yourself. We can also combine it with functions from the raised DSL. So I feel that this is very much in line of the spirit of the Kotlin structured concurrency DSL and many other DSLs that we find out there. Finally, a very commonly asked question is, how does race interact with third-party DSLs? And the Kotlin language defines a contract around cancellation exception, which says that if your coroutine cancels itself, it needs to throw cancellation exception to signal this to the outside world. So this is exactly the contract that we need to respect also with the race type. So if an error occurs in race, we need to raise or throw a cancellation exception such that the outside world can see our failure. And in this case, it will make the transaction roll back. So it behaves exactly the same as we would expect otherwise. And it is really, really powerful, but that gives us automatic interrupt with all the other DSLs that you find in the Kotlin ecosystem. So, to conclude, typed error handling is really powerful, and it allows you to compile time check errors in your unhappy path if and when you want to. You can bring your third-party types, so you can also define DSLs on top of race for your own types. It brings automatic interrupt with the rest of the ecosystem thanks to the cancellation exception contract in the Kotlin language. I think it fits elegantly into the rest of the ecosystem because we cannot find a single technique that is not used in the Kotlin standard library or Kotlin coroutines. And while not shown today, there's many different ways of dealing with trace for different strategies like error accumulation for error reporting or validation. So we've covered the standard library. Arrow also offers other utilities on top of Kotlin coroutines. For example, the resource type is like the AutoClose DSL, but with support for suspension. The FX coroutines module offers high-level DSLs for parallel operations, racing, but also concurrent data types like countdown latch and cyclical barrier you might be missing from Java concurrent. Also has a collectors API for building powerful, complex data pipeline transformations on top of Kotlin coroutines. There's also a software transactional memory module that you can use to replace atomics in an imperative DSL to prevent deadlocks, but that's probably an entire talk on its own. But today I want to focus on resilience. We're in our user premium registration flow, and we want to make sure that we can get the user to a smooth user experience and get him to his payment as quickly as possible. So here is what could be a vanilla snippet in Kotlin for an exponential backoff with a max retries. And this code is quite complex, right? We can see we have multiple mutable variables, we have a non-null casting unsafely at the bottom, we have an infinite while loop, we have breakpoints. It's in general quite complex to read. The only thing that we really cared about is our insert user function and catching an SQL exception and attempting to retry. So this is what the same code looks like using the error resilience schedule type. So we define an exponential schedule for any SQL exception that might have occurred with a given base delay. We can then compose that with a schedule that retries for a max retries amount of time. And we then simply call the retry function and call the function we want to retry inside. So here we have effectively decoupled the schedule, which is an immutable description, from the code that we want to retry. But retrying is very tricky. And typically we have to evolve or retrying code over time. And when we are working in heavily distributed systems, well, if a service is overloaded, we should typically not try to retry with exact retries. So we prefer to introduce some randomness or jitter in our backoff policy so that we do not work with exact intervals. We can very simply do that with jitter function. But not all SQL exceptions can be retried. So sometimes we want to compose a predicate to say you have to continue running while my predicate returns true. And once the predicate returns false, the SQL exception will be rethrown and the schedule will stop retrying. But a schedule can also be reused for retrying typed error handling. So we can simply replace our SQL exception with a typed error that does not participate in the throwable hierarchy, and we can use retry raise to retry any typed error code that we have. For example, our receive payment method from before. And schedules can be reused for even more than that. So for those that are familiar with the Kotlin standard library repeat function, a schedule can also be used for repetition. And in this example, and I hope you don't have this use case too often, if you have to work with a flaky service or a legacy system, sometimes you need to poll regularly until you get the desired results. So here, I know for my flaky service, after about 3 attempts, I get a correct answer, so I'm going to every time try for at least 5 times. So, to conclude, a schedule allows us to very easily split our scheduling policy from our logic. And it allows very easily for building very complex schedules just by using the builder methods. It can be reused for repetition and retrying both exceptions and typed error handling. So the schedule is extremely flexible, and you can use it to define common policies and share them in your entire application. And as a bonus, it is an immutable description, so it is completely stateless, so you can pass it around or inject it for testing. But since it's built on Kotlin Coroutines, it also supports Kotlin Coroutines testing. And furthermore, it also has integration for retrying Kotlin flows. There is one more concern in our user premium registration flow. When we insert the user and the payment is not handled correctly, the user needs to be rolled back. Right? The user cannot remain a premium user if no payment happens. The problem here is that inserting our user happens in the database, and our received payment is a third-party service. So we are dealing with kind of a distributed transaction, which is always bad. So we have 2 commonly used options, which is either a transaction or the Saga distributed transaction pattern. We're going to cover both, but I'm going to start with the Saga. So I like small functions that do one thing really well. So I'm going to wrap my insert user function, and I'm going to add the Saga capabilities to it. And we do that here by introducing the Saga scope into the context parameter. You might have guessed, the Saga scope is an interface with a single abstract method, the Saga method. And the Saga method takes two lambdas. The first lambda is the code that we want to execute, and the second lambda is the rollback or the compensating action. So in case our Saga DSL fails, the delete user function will run. Keep in mind here that this does not give you the same guarantees as a transaction, since the delete user function can eventually fail. But both Saga and transactions have a lot of trade-offs. So we can replace our insert user function with the insert user or rollback function, but now our code does not compile. Our insert user or rollback function requires a Saga scope, and it's nowhere present inside. So we can introduce a Saga block for the scope that we want, in this case, inserting the user and receiving the payment, and we then run it as a transaction. In case anything goes wrong, the compensating action to delete the user will run. So here we keep our transaction as small as possible. But another commonly used technique is to wrap your entire route in a transaction. And I'm not going to discuss the trade-offs, but I'm just going to show you how you can achieve this in a type-safe way. So we can introduce a transaction type in our context parameter. And the function body is reverted to the original implementation. And this is already possible today, because the transaction type comes from the exposed ORM JetBrains library. But the same exact technique is applicable to the SQLite library as well. So now that we've defined these functions, how do you eventually call them in your route? So here I have a Ktor route where we are calling our function, and the Ktor implementation is irrelevant. But if you look at the body here, we have to provide two things. Our race context, which we provide by providing the error handler, and we need to create a new transaction, which here we use the new suspended transaction function from the exposed library. So now we have the race context, the transaction context available, so we can call our function. And again, if you've worked with the exposed library, you might see that this might already look like a lot of code that you're writing today. One thing that I want to emphasize is that the order of the raise and the transaction matters, but the same rules apply to exceptions. If you handle your errors or your exceptions inside of the transaction, it will never roll back because it doesn't see anything going wrong. So if you want your transaction to roll back, you need to handle the exception or the error outside of the transaction, such that the transaction can see the error or the exception. Right? So we can use the exact same patterns for many things that already exist in the library, just exposed, SQLite. Earlier we saw flow collector from Kotlin Coroutines. So we can see that these patterns are already everywhere in the Kotlin ecosystem. So to conclude, the Saga DSL gives us a very elegant way of dealing with the Saga distributed pattern. But I want to emphasize again that distributed transactions are not ideal and should be avoided wherever possible. But I also want to emphasize that all the DSLs that we've seen are extremely optimized and efficient, so you can build your own systems on top by combining these different DSLs. So that brings us to the final topic, immutable data. And I think immutable data is important to all of us. Whether you're doing Android or working on the backend, everybody's using immutable data these days. So we've seen Arrow Core complementing the standard library. We've seen ArrowFX complementing Kotlin Coroutines. When we think about immutable data, or at least I typically think about data classes, sealed classes, vals, and maybe read-only collections. So in my opinion, that is more related to the language rather than the standard library. So I think ArrowOptics complements the language. And it's kind of a standalone project, and it has 3 small integrations. 2 for avoiding boilerplate using KSP or GVM reflection, and there's a small integration library for Compose to more elegantly work with view models and immutable data. So as an example, we're going to use 2 data classes, a product with an ID and a price, and an order item with the product and the quantity. So here we have our order item, and we copy the product, we copy the item, we copy the inner product, and we can then finally apply a 10% discount on the inner price. But even though we only had 1 level of nesting, we can already see again that some callback nesting is being introduced. And we can solve this again with a DSL. So the Arrow Optics DSL allows us to define a path in our data, in this case from the order item into the product, and from the product into the price, and then it allows us to call the modify function to modify an existing item and apply a function to the path in the data. But Arrow Optics can do a lot more. Arrow Optics also has support for collections. So in this case, you have an inventory data class, and there's a collection of products. And since we just gave a discount, we need to increase prices. So we copy the inventory, and we map over every item in the list of products. We copy every product, and we apply a price increase. But now we've introduced Collections API and logic into our copy stuff, and I don't really like that. So we can solve this again with the Arrow Optics cell in almost exact same way as before. So we define a path from the inventory into all of the items, and from all of the items into every item, and from every item into every item's price. We can then call the modify function on that path, modify a value, and apply a function to it. But we can even go beyond that with Optics, since we also have support for sealed hierarchies. So here we have a simple sealed hierarchy, error or product, and it can be success or failed. And if we want to then apply a discount, we need to drill into the subtypes using a when block. And in the success case, we can drill into the inner product and apply a modification to the price by copying the product. So you can see that this is even worse than before, and we just want to simply update a single value. So the Optics DSL can again solve that in almost the exact same way as before. So we define a path in our data from the sealed type into one of its subtypes, into the inner product, into its price, and we then can apply a function to the sealed class type by modifying the inner price. And this is really, really powerful because we have again split the path from the value and the logic we want to apply to it. But sometimes we need to modify many values at once. So recently we've introduced the copy DSL. And the copy DSL allows you to update a value directly, and it allows you to apply optics paths inside of the copy block. Right, so this makes it even more elegant. So to conclude, I think that optics really allow us to focus on our business logic and allow us to separate the paths in our data from the logic. That allows us to avoid all the complexity in between. It also allows us thus to simplify very complex immutable transformations, as all the different techniques we see today can be composed in more elaborate ways. But I truly think this belongs in the language. Because like I said in the beginning, I think immutable data is a concern for all of us. And I've heard from many people that they don't feel comfortable defining very deeply or complex nested structure because that makes updating them very annoying and complex. So if we have first-party support for this in the language, that barrier will disappear and we can freely model our models however we want. And it seems that Roman Elizarov, based on the KEEP and the U-Track issue, and Alejandro Sorana from his talk last year seem to agree with this idea that updating immutable data should be easier in Kotlin. So I really hope that next year or the year after, we can have a really nice announcement about this. So, to conclude, what did we learn? I think we've seen that Kotlin really, really loves DSLs. And Arrow really loves Kotlin for it. Right? And I think these things really work nicely together. I hope I've also been able to show you that Arrow tries to offer small and feature-specific modules so that you can plug and play what you want and when you want it. But there is also much more to learn. So, if you're not yet on the Kotlin Slack, I want to invite you there because there's many people from all different kinds of communities in the Kotlin community. The Arrow channel is extremely filled with Arrow users and contributors that you can ask and interact with on a daily basis. I also want to share again the website which we've been continuously trying to improve over the last year. Within the Arrow organization, you can find many different projects besides the Arrow main repository. I already uploaded my slides of today. In case you've missed anything, you can find everything back in the link. And all the code that we've seen today is also already on my GitHub. And I've uploaded in 3 different flavors, using context receivers, without context receivers, and using the traditional either type. So you can compare these different styles with each other. It's also backed with a real database and cater, so it's like a real live production example. Finally, I also want to thank all 295 contributors in the current main repository, and I hope I did not forget anyone, so I want to thank everyone in the Kotlin and Arrow community for being so supportive and being so amazing. And finally, I want to thank you all again for coming to my talk. Please do not forget to vote, and I'll be happy to answer any more of your questions.